Hello, everybody. How are all of you? We are back for topic 8 of C as an additional language with the Enceladiosaurus, who's on the line. You there?
Hi, everyone.
Hello. Maybe I got the accent in the right place, too. So, hello, chat. We're just doing a little warm-up here. We went over some we missed last week, although a bunch of you came by for adding manual pages. I don't have that version of the code deployed tonight because we didn't have time to look at WebSockets and all sorts of other boring details. But we're moving beyond that. We are just getting down and dirty with C. We are going to get back to dynamic memory allocation. And one of the things we sort of briefly went over previously was how to parse and read text stuff in ASCII text, nothing too crazy, but from the file system. And today we're going to use that same data. We're going to go a little deeper. So for those of you who've seen the web page, I think you all know what's there, but I'll find this thing. And yay. All right, cool. There it is. So this has, we're doing topic 8 here, and I'm going to just ignore this data. So I took some dry, boring, dull census data, which is very important for your country. Fill out the census if it's been mailed to you, but all that PSA stuff. But we're going to we're going to go back to this planetary data, and we're going to start messing around with that in binary length. So got the glove. We're ready to draw things, and I think Jesse is ready to learn stuff. So we have our shared editor up, and let me just pull up our whiteboard. Sweet. Okay, and by the way, for those of you who don't know, that was a real 20. I rolled that 20. Jessie is my witness. She was on while I rolled it. The camera was live, so you can go check. That's a real 20. It's legit. All right. And because it's a real 20, that means we're going to do hard topics today because the luck is with us. So let's get ourselves another color. And let's just leap off. Oh, that's fun. All right. So
ooh, yeah, that stands out.
Yeah. I should use that color more often. So binary IO. So that's and then over here, let's choose another fun color. This is going to be our allocate. Oh, that's too dark. Dark and dismal, no fun. Allocators. So this is dynamic memory. So this is kind of like where C really, like, the training wheels come off. So this is there's nothing harder, I think, to talk about in C than dynamic memory and all of the fun associated with it. But we're going to get to that a little bit later. So for right now, we did a little bit of binary IO, and do you remember how we opened files and got references to them?
Yes. So that was not last week. I think that was the week before.
Yeah, it's been a little while.
So it's been a little bit, but I'm trying to remember how we did that. So this was with like fopen.
Yes,
and,
exactly. Exactly, that's fopen.
fget-s and things like that, right?
fget-s for reading things. This would read a line at a time, assuming you had enough buffer space for it. And then we had fclose to sort of wrap that file up. And this actually inherently causes the file to flush its stream. So if you have some data that hasn't been written, this kind of guarantees that it gets written. So when we did fopen, we specified some stuff, and the calling stuff that we did, we sort of said like, okay, fopen, and then we set a file name, so there's some file.txt or something like that. And we specified a open specifier, and this is the same as it is in Python and most Unix systems. So we just specified we wanted it open for reading. And this returned for us something very un-Pythonic. We got back a file pointer, and we can just call it fp for the moment. And this is sort of valid. So actually, it's not sort of valid. It should be totally valid, assuming your file system doesn't have a problem with uppercase letters. But C doesn't really get into that kind of thing. Great. Well, this is sort of the part we're going to mess around with today. So when we opened this up, we intentionally did not specify anything else. We just said we want this thing open for reading. And that's cool because we can say this is reading. We can also open something for writing, which we also did the other time. Last week or the week before, or sorry, the week before or the week before that. And one that we didn't really touch on, but it's there anyway. So for completeness, I'll just mention there's A for appending. And this is sort of the same thing as writing, but instead of writing will, if the file already exists, it'll just delete it. It's like delete and open. And that'll be like, so it's like you're opening this thing for writing, like you fully expect to start from scratch. And appending is really, if it's already, if there's nothing there, then it's really the same as opening it for writing. But if there is something already there, then this will just stick it at the end. So this will start at the end. And the only real difference between these two is the position in the file. So in this case, like it's actually, the position is 0. It's starting right at the beginning and it's making sure that there's nothing after it. In this case, it's whatever the end of the file is, and it's going to say, all right, let's just start adding stuff on there. So if you want to be careful, generally open things with the A permission. If you really want to make sure that there's nothing there, then open it with the W permission. But that's all pretty straightforward, and I think it's pretty much the same in Python.
Yep, pretty much.
Okay. Now, the other specifier we can add, which also, it's funny, Python borrowed it as well, is we can add some other stuff here, which we can say, we can tack on a B. Have you seen that in Python?
Mm-hmm. Yep.
Okay, cool. So this implies binary, so we do not want you to interpret. So this is basically do not assume anything about the data that's in there. So just assume that it is just raw data and we're going to operate on it as raw data, which means we are not going to do things like fgetS. We are not going to do things like fputS. These imply that I'm working with strings and text stuff. But instead, we're going to be using binary operators, and those are fread and fwrite. And they're basically reciprocal. And again, you'll get permission violations if you try to do an fwrite on something that's open for reading, and same thing if you do fread on something that's open for writing. Bad stuff usually happens. So, try to open with one permission. There is a further modifier you can add, which is you can tack a plus on the end, and that means reading and writing.
Yep.
But we're
Same
not
in Python.
Yeah, we're not. Well, yeah, Python stole it. Which was the right thing to. Oh, and hey, what's up, Loafbone? Sorry, I just saw you. I guess NC already saw you. Okay, so fread and fwrite. Well, what do they do? I mean, in a nutshell, they read. It's sort of like fgetS in that you need to say how much, but you also have to say where. And keep in mind that this is no longer structured, right? So this is not a character string. Like with fgetS, we can kind of always assume we're dealing with some sort of char pointer. And with this, we could make it a char pointer. I think the actual specification is for a void pointer. And this just basically means I'm not telling you what type it is. It's a type, and it's definitely a pointer, but if you want to get into that, you're going to have to cast it to something else. So you're going to have to say this is a stream of ints, or this is a bunch of floats, or whatever you want to cast it to. But we better keep that pointer there as well.
So quick question, actually, because we've used void before, and my understanding of it is just based kind of situationally on using it to define functions, like the return of a function being a void, meaning kind of nothing.
Yeah.
But in this case, having a void pointer, that doesn't quite track for me, just because how do you point to nothing?
Well, so it's not, in this case, we're overloading the use a little bit, but it doesn't mean nothing. It means no semantics. So if you're operating with a character, like for example in here when you're dealing with like a char, if you're doing like an unsigned char, or pretty much, or a byte on some operating system. Well, let's see, I was just working on Nintendo stuff, so it was bytes over there. But these all have semantics kind of associated with them. Like I plan on dealing with this as sort of textual data. But and if I throw an int specifier or a float specifier on it, I'm sort of hinting to the compiler, like, you know, on most systems that we're dealing with nowadays, these are going to be 4-byte chunks, and, you know, each one of them is going to be, you know, follow float rules. So I'm going to have, like, the significand and the mantissa, and I'm going to follow float sorts of semantics. With an integer, it's just numeric, you know, it's numeric round numbers. And in the case of a void pointer, I'm telling you no semantics. So if I try to do any sort of operation that implies anything about the type, the compiler's going to scream at you.
So what? I'm still kind of having trouble conceptualizing that. So if you don't have any semantics, and if you can't make any assumptions about data type, what's left? Well,
you have to make the assumptions. You have to explicitly cast it. So you can say, like, this is a void pointer, but it's really a char pointer. So I'm going to cast it up. So this is kind of like up to you as the programmer to say, like, I am now putting semantics on top of that. I want you to treat this as character data. But
why wouldn't you just...
Because I don't know what was written to that file.
I see. Okay.
So in the case of like fread or fwrite, I don't know what kind of data was written there. So I can't give you any semantics until you explicitly say this is really integer data or whatever.
I follow you there, but I guess, you know, I'm getting really used to this kind of C aspect of needing to know some of that, like specifying how much memory and whatnot. How do you point? Because, you know, pointer being to a memory address, right?
Yep.
So how do you point to an address in memory if you don't know how much memory you need because you don't know the data
There you go.
type?
How big is a pointer?
Or how, I mean, in this case, like for having a void anything, like how does the computer know how much memory to allocate for that?
Wait. How big is a pointer?
Well, pointer's as big as any address in memory.
It's not related to the underlying type.
So, but so the way that we've dealt with it so far, right, is that you're pointing to a memory address for something that exists. And so the thing that's kind of tripping me up here is like, it's almost like a placeholder.
Yeah.
Is what it feels like. And that's fine. But then how do you put a like the thing that I've learned in C, right? You can't really have placeholders because you need to know how much memory you need. So how do we know how much memory we need?
fread and fwrite
in memory
do exactly that. They say, how much do you need? You have to explicitly say, this is this size. Because there's no semantics there on the void pointer. The void pointer itself has no idea what the size is. It doesn't know how to deal with any of the types. In fact, it's intentionally untyped. The only thing, a void is not a standalone type at all. I can't declare something as void.
Yeah, that wouldn't make sense.
I mean, I can't say like void X. I mean, it's like, how big is X? Like, what?
Okay, so you have specified how much memory you need, and it's just that we're leaving it kind of data type neutral or semantically neutral.
Exactly.
Except that makes sense.
I can't define a void of a thing, but I can define a void pointer of a thing.
That makes,
Because this is the same size no matter what the type is, right? So
because it's just it depends on your memory.
It's really just saying this is an address in memory. It's not saying anything about the semantics of that memory.
Okay. Yes. Follow me. That makes perfect sense.
That's kind of important because when we're dealing with a file, how did we store it? So when we were using, you know, fgetS and fputS, the semantics are clear. We're talking about text. So this is character data. And in particular, it's going to be character arrays. So that's like very clear to the compiler. But in the case of void, in the case of binary data, the C standard doesn't know all the different ways you're going to be writing and reading binary data. In fact, the most common case is you're going to be writing and reading structs. And your file format, they don't have any, you know, idea of what you're going to do with that file format. You might decide to write like a character that's a string that's 10 bytes long, and then you write a struct that's like 5 bytes long, and then you write, that's up to you. It's up to you how you want to serialize your data or deserialize it. So, and yeah, Strophium's going, void pointer is like photo of a UFO. I don't know what it is, but here's where it is. That's
a very interesting metaphor. I kind of like that.
I like that. Yeah, and that really like focuses on the fact that it's a pointer. It's not a thing. So I don't know what is going to be there until I take the time to cast it. So casting is your job as the coder. Like if you want semantics and you want to start dealing with this data, you should probably cast. In fact, when you have a void pointer, you should treat it, I wouldn't treat it like a UFO. I would treat it like you're holding plutonium. Like, don't do that. Like as quick as possible, know what you're holding. I mean, like this could be radioactive, like, so type that thing as quick as you can in your code. Now that's kind of guy editorial. It's not required by the C standard, but good practice is you're probably going to want to type it as quickly as possible so that the compiler will prevent you from doing bad things with it.
That makes sense.
Okay, so, well, what do we do with this binary data? We're going to start the same way we did last week, and we're going to write something out first, which is going to be the thing that we want to, operate on when we're going to be reading it back in. So, I don't really want to write out text data with this. I mean, I could use fwrite on text, right? I could take my char pointer, which is pointing at something, and I could cast it to void pointer and say, all right, write this thing out as binary. Like, that's totally fine. I could do that. But we already have a whole bunch of text operations for it, so we're not usually going to use this. We're typically going to be using things like structs. So today we'll be focusing mostly on using it for a struct. So in our case, we were doing struct planet, and we had, I'm going to keep the same thing sort of as what we were doing before. So in this case, we were doing, characters, and the name was 10 big, and the period, the orbital period is just a normal float. Now, this structure is something that I can write out as binary because this has some representation in memory. And I'm partially setting you up here, and it's because of a fact we very lightly touched on, so I apologize in advance, but we're going to work through that in the actual code. But the important thing that we need to know here is that this has a definite size, right? This particular struct planet has a definite size, and what operator do we use to figure out what the compiler assigned it?
Was that Malloc?
Well, Malloc is when we were doing it dynamically, but I mean, how do we tell how big a type is?
Oh, just size of.
Exactly. So we can say size of and this thing.
Right, and I remember this being a little confusing last time, just that the memory that it allocates was not what was intuitive.
Yeah, that's exactly the setup.
Yeah. So I remember kind of us looking at
and we're going to look at
the assumptions that we have about memory.
Yep.
Because it was, assuming that if you have kind of like a certain type, a data type that has a certain size and a different data type that has a different size, like we would think maybe just add them together or take the bigger size or something. And I remember it not being quite as intuitive as I had hoped.
Yep, it's not. And so you're right to think about that. And that's exactly what we're going to look at before we go messing around with this thing, because I told you before it's going to matter. Well, this is where it really matters. So in our case, excuse me, throat's kind of whatever today. So fwrite, I didn't fully tell you yet, but fwrite and fread are basically the same thing, and they're going to work the way you just sort of said earlier. So fwrite takes, and we can look this up in man pages, but basically you got to give it some sort of void pointer, which is this is going to be the thing, and then you have to pass along how big is it? Well, how big is each element? So let's call this each element size. And then there's sort of a how many elements, and and then obviously where you want to write it to. So there's a file pointer, which is where. Okay, so that's fwrite. Fread is very similar, and we'll get to that a little bit later after we get through our fwriting. But fread basically is going to take another void pointer, which is this is where you're going to get your result when you're done reading it, and it's going to take each element size again. In this case, they were very consistent in the library, so you don't have to worry about like kind of screwy parameter order. And again, how many elements? This is the same, and again, a file pointer, which is where. So this is all basically identical when you're reading and writing. And that's a little different from some of the string operations, but that's okay. So does that kind of make sense? This is the high level?
Yes, I think it just, and the fwrite requirements make a lot of sense to me, but at least with fread, I think the difficulty there is it requires you to know so much up front when I can imagine there are
semantics.
Yeah, and I can imagine there are situations where you don't know a lot about the data file that you want to look at. And so I wonder how you would handle situations like that.
That's exactly the obfuscating detail a lot of C programmers use intentionally. Games would hide data like this, like they intentionally did not want their data structures to be obvious to read, because they were worried about it. So, really that's kind of the wrong approach, because you really should be encrypting things, and but anyway, back in the C era, they were like, if I write the file format to be all screwy, then no one will figure it out, and I'll be hack proof. And that was ridiculous. What fake donate? What?
I don't know, but somebody is fake donating you
$10,000 for 10 grand Etor Pepsi of fake donate. I appreciate it. We're rich! Yay!
Yay!
And Nathaniel's right. This was sort of that era that they refer to as kind of, well, actually, I shouldn't say that era. It's still the case, but they did believe that this is a case. Have you heard the term security through obscurity?
Yep.
Okay, so that's basically that.
And I don't like it.
So yes, you are right. It does need more stuff because the myriad combinations you can use these things is vast. You can go fwriting, a struct planet 1 minute, and then you could fwrite a char the next moment, and then you could fwrite another struct, and then you could, whatever you want to do. Like it's all your choice with this, but you're going to have to undo whatever you did when you read it back in.
I think it's interesting because, and this is just maybe era differences or whatnot, is that there's such, and I think rightly so, such a focus nowadays, at least, on, truly, like, you're an okay programmer if you write code that you can understand, but like you kind of level up, if you will, if you write code that is understandable by many people. Yeah. And so it's interesting mentality. Because it's a different mentality, and there's a lot more focus, especially I think on a lot of development teams that I've worked on, where you're there to make your code as readable and explainable and accessible as possible. And so it's interesting that so many of these features, as we talk about them, are kind of designed for the opposite. Designed to kind of like obscure things or to hide things. And understandably so for like proprietary stuff, but it's just interesting.
Yeah, I'm going to tell you a trade secret. Back in the day, they used to try to make your code as unreadable as possible because that meant they could never fire you. That was a prevalent mentality at DEC. At like there were a lot of companies where that like exactly the opposite of what you're talking about. Like the open source movement hadn't started yet. Things were very proprietary and a trade secret, and anyway, different.
That's really interesting though too, because I think
it wasn't the open source era. I can tell you that.
Yeah, such a shift in mentality is that,
Nathaniel
when I'm writing
still
code,
exists.
At least at work, like thinking a lot about the next person that's going to improve this or need to read it or understand it.
Yep.
So trying to have as thorough and readable documentation as possible, and have very intuitive, readable code. And so it's it's interesting.
Yep.
It's a very different mindset.
This
So.
standard was written a long time before that.
So the standard that you often talk about us using was written before I was born.
Yep.
So
yeah. So
yep.
computers were different.
See.
Digital was a thing. The DEC was a company. So, rip DEC. Long live DEC. DEC is dead. Okay, so we still have Octal to deal with. Anyway, we'll get to that later. So DEC left us a few GIFs. Which we're going to talk about in future episodes. I'll let Last Miles get into that, actually, because that's really his cup of tea. So anyway, great. Let's set up a structure. Let's assign a couple planets. Do you remember how to make an array? I know we did arrays kind of quickly, but it's pretty much the same as Python, so you know how to make an array. So in main, give me an array of planets. I don't know, call it P.
Okay, an array of planets.
Yeah.
Okay. So, and I'm sorry, you said make it a main. So an array of, hold on. Yes, okay, fine. So are these going to be, I should know, are these going to be planet names or like planet?
Oh, no, I want to use this struct planet thing we got. They're going to be.
How do you make a?
Okay, well, start with a single one.
How do you make an array of structs?
Okay, start with a single one.
A single what?
A single planet.
Okay. So let's just say that we're going to call this planet Bob.
Bob. Nice. Okay.
Okay.
And array operator.
Oh, yep. Well.
It goes in the usual place.
Okay.
Now we have the Bobs.
These are Bobs.
Okay, so yeah, nice. And we can pluralize it if we want. Okay, now C is going to require a size because it doesn't know how to figure out from this code how many planets to allocate space for. So
okay,
let's give it 3.
And so the 3 there, it's going to know to take whatever the, yes, okay. Nope, ignore me. I'm good.
No, I'm not ignoring you because that's exactly the next thing we're going to do is how allocate what?
Mm-hmm. But I think so since we've already defined the struct planet, right? It's going to work just like char, creating a string which is an array of chars, right? That data type, struct planet, is already defined. And so that size is then also already defined.
And how do we get that size?
Size of.
Let's get it.
What would you like me to do with it?
Print it out on the output.
Okay.
Very nice. And new lines. We got to get
Starting to remember.
Yeah. There's no Python here.
Size of planet. No, we just want planet. So can I just reference it as planet or do I need to say struct planet?
Struct. You always have to say struct.
Okay, just
until I teach you how not to say struct, but that
right.
there's a dirty trick we're going to get to a little bit later. But
yes,
I don't
like dirty
tricks. That dirty tricks is basically the next episode. That's topic 9.
Dirty tricks. All right.
So we're trying to do the pure C up until like the last episode of that. But
we're like now we're going to learn the fun
okay, now the rest of it.
You paid your dues.
Yes, you paid your dues. You've written enough good C, so now it's time for the dark side. So.
Yes.
Okay. So we know that the size of this is 16. And that's a little funny because if we knew that a float was the same size as an int.
Doing some math in my head. That seems awfully.
Because we can run that and it's still the same size because a float is the same size as an int. And an int was how big on this system?
32.
You got it. So
4 in this case,
so
because
4.
it's size of gives us bytes, bytes. There we go. Whatever the 8 one is.
Exactly.
Yeah. And so this is technically 6 times 8 bits, right?
6 times 8.
No.
What
am I thinking of?
Wait. We have the int. Oh, wait. Take this apart. So the O period here is how big?
32.
Right. Well, use bytes.
Bytes, yeah. Or 4. Sorry.
Yeah, it's 4. Okay, so that's 4 bytes. And how big is a character?
6. No, 8. 1.
Yep.
Yes.
Yes, correct. It's 1 byte. So 10 of them is
10.
10. So 10 plus 4 is 16. Because C.
Rounding up in multiples of 8.
It has to do with padding, which we touched very briefly.
Yes.
And
because of how like the memory is organized,
alignment.
right?
Yes, that's correct.
Yeah. Okay.
Yep.
I remember that.
So
vaguely.
that's important here because when we write this thing out, our file bytes are different from like RAM bytes in that like, every.
But we can do, sorry, really quick. Am I remembering this correctly? That we can do like, oh, I'm going to butcher this. It's like, I remember it having underscores, like attribute, and then we can say like, not stacked. It's like packed.
Yes. Yeah.
And we can say that.
Usually we put a space here, but that's perfect, by the way. Like.
And that's going to prevent the memory padding.
Run that.
Okay. Oh, nope. Maybe. Hold on. I think there's supposed to be 2, maybe.
Yeah.
There we go.
Awesome.
Right. And so that's what gets rid of the padding.
And that changes, yes, that gets rid of the padding. So now RAM is going to be matching kind of like what we expect. Now, that's really important when we're talking about disk, because disk storage, we don't waste bytes on padding on disk, right? That would be a crappy use of memory that, back in the day was like punch cards or something. You know what I mean? So like we really don't want to like throw away memory on persistent storage. We don't really want to throw it away in RAM either, but there's sort of a trade-off. Padding gives you a trade-off between speed of access and, which is why it's aligned for the microprocessor architecture versus like it takes a little bit more space.
Just a tiny bit more. So why does padding allow for greater speed? Is it just because, so horrible metaphor incoming, but thinking of kind of pointers and memory locations as like physical addresses, right? Like each address points to a house, and that house is on a plot of land. And like, let's say we have, oh God, this is going to get bad. Like 500 units of furniture or something. And maybe that's enough to fit like a full house and then like maybe a little bit more. But it would make sense for like the memory to point to like 2 separate houses to make it easier to access versus to like start a new house's furniture in the second house. Does that make any sense?
Maybe. I'm not 100% on that one.
In my head that kind of makes sense is like
you made me think of one that might be related to that, which is like if you ever played that game with like you're coming up on like an escalator and you're like kind of timing how long your stride has to be so that you hit the escalator when you're like like you want it to be like a flowing smooth motion, right? You kind of get on the escalator with like a natural stride as opposed to being one of those people that like stops at the escalator and waits for the stair and then like steps on it, like like you don't want to be them, right?
But what is so you kind of said that it has to do with the microprocessor architecture processor something. I forget what you said, but like something about the architecture means that if we keep things padded, like in my head almost like new lines, it's easier or it's faster to read, but then or to access. But why is it faster to kind of access a new line or new, like you always use this sort of picture of little horizontal rectangles stacked. So why is it so much faster for a computer to start at the beginning of the horizontal rectangle versus start in the middle?
Because
like it seems to me that it wouldn't make a difference.
It was designed to.
But why?
that has to do with reasons that we're going to have to just get into hardware to do.
No worries.
But it literally comes down to like kind of like some architecture choices that they made specifically for like how much data they were typically accessing for speed. Like, so for example, like as the standards started to sort of settle and, typically we were pulling blocks of 4 for ints from memory. That was a very common operation. Then it made sense to make processors that were really fast at pulling a block of 4.
So it was just like, at the start when building these processors,
they were typically aligned for like 8 bits.
This one kind of unit of data, and as data types diversified, that became less efficient.
No, there was no standard in the beginning.
So, no, I don't mean like standard. I just mean that.
No, I'm saying there was no agreement on what a reasonable amount of data was. Is kind of the problem. Like so some companies are like
units of the data.
Yeah.
Right. So like if the units of the data, like it's base 8 or base 4, if you will, right? And so then it doesn't really matter how wide your stack is per se, as long as it's in units of 4 or 8 or whatever your data
Yes, but I
type
feel
is,
like
right?
we should really talk about this at the talk session.
Okay.
Because this is gonna be a long one, I have a feeling. But so I'll just call it data access and alignment.
31-bit architect. Okay, hold on.
Yeah.
I'm gonna.
Yeah, there's 12-bit architectures. There's a lot of the common ones were like 8 bits or 16 bits.
That makes sense.
Sometimes they were
Everything seems to be
24-bit. People were like, oh, well, RGB, each thing is 8 bits, so we're going to align on. Again, you have different trades, and it kind of comes down to cost at the end of the day. I mean, you could make something that could read everything equally fast, and then alignment isn't an issue. So alignment strongly has to do with your chip architecture, because it has to do with how the hardware designers design it. But we're going to go into more detail on that later.
No worries. I don't mean to derail. I think like sometimes knowing those details of why something's done helps me understand how to use it.
Yep.
But I'll put a pin in that for later.
Pinned.
Pinned.
I'm not calling this talk topics. I'm calling this pinned topics. Okay. So, Josh Perry.
All right. So to get back to this, we were talking about the attribute packed, which helps get rid of the padding. And the reason why it's 16, not 14, is because there was that padding to help it align better for speed in our stack.
It does matter in
dimensions.
architecture. This is kind of like one of those like sort of leaky details of the compiler, because C has no real opinion on this. Like C was trying to be something that was portable to all architectures. So they didn't want to get into like what the chip designers were going to do. So you could make up your own C compiler and align this however you want. You could have a C compiler that never pads if you want.
Okay.
You'll have to implement it. But, all right. So theory aside, we now know that the size of a planet is 14 when we're sort of dropping our padding. And that's GCC. That was our first compiler directive. So how do we fill out a couple planets here in this array? How do we get some bobs?
So in that case, we could. So this is where the idea of having an. No, I got this. I think I got this. Hold on. So you could kind of like start here, right? We can set the first element of our array of structs.
Mm-hmm.
Actually, hold your horses. Let's say that we've got
a Bob 1,
a singular Bob, and so we can say that this is Bob 1, right?
No.
No. Well, there goes my understanding. All right, no, I'm still kind of struggling mentally with this idea of having an array of structures. Like, from a Python perspective, it makes sense, but from a C perspective, it doesn't. Okay. So how to interact with it and assign elements of the array of structures is
okay. So
kinda...
how do we? This refers to the first Bob, right? Mm-hmm. And when I'm in a particular, like when I've just got a normal, forget about the array for a moment.
Oh, I got can we do? I'm sorry.
Yep.
Can we do like?
Yes. Exactly.
That? Gotcha. Okay.
Except it's another array because it's a char type. So how do we deal with putting stuff in arrays, into character arrays? Can
I cheat? Will you let me cheat?
What's cheating?
Oh, like leaving the brackets, because I remember when we first learned that
No,
that was a...
No, it's already been declared. That doesn't work. Okay. That only works at definition time, like when you declare the thing. You don't get to do that later on.
Okay,
you can try.
Because name is already 10, right? So when you
sure.
But when you said that it's another array.
Yep.
What were you getting at?
Because this would really be like
M, exactly, right. So, can I just put a colon?
What do you mean colon?
Because that's absurd.
Which is why we have a string copy routine, right? We don't normally do this with strings.
Right. Okay. So, thank you. It's that I've been coding in Python all day. And so
we got to break
switch
that
sometimes for well, I can't break that. That's my job. But the nighttime switch to C sometimes, like my intuition is still in Python land. Okay, so string copy. Let me see. That's what I want to copy it into. And then we'll call it Cool Bob. I'm going to make a new planet.
Okay.
It's going to be awesome. All right.
Let's try it.
Okay. Well, so this isn't going to, unless it throws an error, it's not going to change the output because string copy doesn't have an output.
That's okay.
So do you want me to print to make sure that we are copying it appropriately? Okay. So in this case, we want the Bob planet is, and then string, new line, and then Bob's 0 dot name. All right.
Nice.
Yay! Look at that.
Okay, let's go to real planets for a moment that are in this solar system. So we'll just limit the domain a little bit.
And
actually,
chat, stop with the function pointers. We
Yeah.
briefly touched on that last time,
No.
but that is still like here be
ignore,
dragons.
ignore what they're saying because they're.
Oh, I'm ignoring it and I'm telling them to stop.
We're
because
getting
not,
to what they're talking about actually, but we'll.
No.
So
Function pointers very confusing, but yes, okay.
that's okay. We're not doing function pointers today. Don't worry. So,
All right, just the idea of a pointer that points to a function bothers me, so
yeah,
that doesn't make sense.
that's a separate thing. Okay, so
Okay, so yes.
All right. Well, how do we? So you haven't fully initialized this first Bob's because we forgot the O period, right?
Yes. Mm-hmm.
Okay, and so how do we assign O period for it?
Because it's an integer, I don't have to worry about this ridiculous string copy stuff. And so I think I can just do...
Oh, sorry. Let me switch that back to what it should be.
This is going to be... You know what? Bob 0 should be a planet that is very close to its star.
Okay.
So let's talk about... I'm going to go... I'm sorry. 20.5.
Nice. Okay, and if we wanted to add that to our output?
Float. So...
All right, chat. No manually implementing vtables. Knock it off.
Oh, Lord. Words I don't understand.
It's C++ stuff.
That's another language I don't know. Okay, O period.
Well, you're getting to know it. A lot of C++ is C.
Clear this output and
Nice.
look at that.
Okay. Now, this, if we were going to start doing the second planet, we would have to doing it the way you're doing it.
But with 1 instead of 0.
We would do the same thing, but with 1, and then we do the same thing again with 2 for the last one. All right. Well, Nathaniel stole a little bit from what I was going to tell you, but there is a kind of nice way to initialize an array of things. And we already know how to do it with character strings, right? Because we do something like this. We say like, some label, and then we can, do one of these and say some label. And C kind of just does the right thing with that, right?
Yes, and that is because that is a nice feature that you told me was implemented in more recent C, but not in the original C, because you made me do it the hard way the first time.
Yes. Yeah. But
so I remember that.
it does. Well,
I am grateful for the empty brackets.
Yes. It is nice. It's a nice little compile, a little bit of syntactic sugar, not the salt that we were talking about last time. But but using that same concept, we're basically assigning an array in this one line. Right, because we're assigning S and then O and then M and then E and then space, right? We're going one by one and assigning that to each of the elements of some label, right? So we can do kind of the same thing with a struct. So I can do something like planet Bob, and I can use this notation, which you might notice from Python because they stole it. But it has a slightly different meaning in Python, but originally it kind of came from this. So I can use this brace, And I can sort of say something like, not cool, Bob. And I can also give it an orbital period that's a little bit longer. So if I run this, I clear my output, I run it, we get a little bit of complaint, except, all right, not cool, Bob is a little bit too long for the 10 characters that we have. So this is a modern compiler
call it
telling
bad
you.
Bob.
What?
Bad Bob.
Bad Bob would probably fit. Oh, bad Bob. You're such a bad Bob. So this is a way of doing a fast initialization with a struct.
Okay.
And
so that implies, though, that you know I'm sorry, I don't know the right term, but like the attributes, if you will, of the struct. So like, for instance, if I were writing a code and defining a struct myself, that would be fine. But if I was using some predefined structs, I would need to know exactly how, or will it accept a partially initialized struct? So if we only initialized it with a name, will it throw an error? Or does it need all of the attributes filled out?
One way to find out, right?
Okay, never mind. All right. Just curious. Like I'm mapping this, and I know this has probably got a lot of like, it isn't a one-to-one comparison, but I'm always going to fall back on sort of references that I'm familiar with to help me understand. And so it's very similar to an object in Python. And so I keep kind of coming back to that a little bit in my mind.
Yep. It's not an object, though. That's C++. But we'll get to that.
Yeah, it's just, that's kind of the understanding that I'm pulling from. So.
And they're using language you should not use, by the way. So don't read about that T word in there. I explicitly mentioned that as something in the dark side that we're going to get to in that last class. But
okay, so that's my reward.
Yeah.
So you guys stop spoiling my rewards.
Yeah,
okay,
no. She gets to write out struct every time for now. Okay, so got to build the habit. All right, great. So this is how we initialize one. Well, guess what? This also works for arrays as well. So I can do this and say this is going to be an array of planet Bobs, and we can start specifying this one at a time because the C initializer is going to be nice to us. And it's basically going to say, all right, you mean that's going to go into the first.
It's a nested struct.
Yes. Well, because it's an array. Okay. It's an array of structs. So this is kind of a short notation of being able to do this all at once.
Excuse me. No, okay, yeah, you got it right. Bad Bob should be much, give it like 127.
Okay. So
the astronomer in me, I'm sorry. I'm like, ooh, no, these are too close. We're talking like collisions. Okay, we're good.
You are totally right. So if we clean up that stuff, then we should have done the fast initialization of a couple planets, and we execute, and it works kind of the way we think it's going to, which is neat. So there's your fast syntax for it. Okay, now that's all beating around the bush, because what we really wanted to get to was serializing this out to a file. Now this is binary data, because while the name is text, the float definitely is not.
Well, the name is text, the float. Yes, okay.
Yeah, the float is stored in memory as a float. Well, in IEEE 754. But I mean, like if I was using an int or some other numeric type, like if it's like a 7, like some control character, it's going to be the equivalent of some control character. It's not in some representation of it. So it's not like a string of the number. It's actually the number itself.
I'm sorry, you've lost me just a touch.
So when we let's think about this as ints for a moment, because we have a little more intuition around ints. So if we just change these types to int real quick, when I store this thing in memory, this doesn't store it as ASCII, right? This doesn't store it as the ASCII number 2 and then the ASCII number 0.
Okay.
Right. It stores it as the number 20, right? So if I look at the bit representation of it, it's going to be, the 16-bit
20 in binary,
plus
right?
the 4-bit plus so it's going to be 20 in binary. So and that's different, right? Because the string is stored in ASCII representation, where A starts at the 65 and B is 66 and so on and so forth. So the numbers have ASCII representations too, but 20's down in kind of the control code area. Okay, so that's this all makes sense, right?
Yes.
Now, if I wanted to save this thing, and by the way, we're going to go back to the float version of it, even though those are both the same type. But if I wanted to write this out to a file, sort of thinking in your Python world, what would you have to do at this point?
Okay, so
I can't just write an object, right?
oh yeah, I feel like you're setting me up for something. But okay,
Just
so thinking about this,
understanding.
if I want to write the features or the attributes or whatever the right word is for structs, if I want to write these parameters to a file, I mean, one, I will say that so far when we have been dealing with reading and writing data, all of the file in the data has been, for the most part, we've been able to treat it as the same type. So we haven't really had to deal with mixed type data. Like even when there were numbers in the first, the data with like companies.
They were textual numbers.
Yes, we read that in as characters.
Yeah, and then we had to turn it into, we used scanf or fscan. We had to actually read it back into a numeric format. But let's say we want to skip that and we want to just write the number out to disk and then read the number back from disk.
Well, so if we're only storing the numbers, I'm guessing that's just like fwrite.
Yeah.
Right? And because we know the data type, we know the size. So we know that parameter, we know how many of them we'll need. We have all of the inputs or the arguments for fwrite that we need, correct?
Yes, but that works exactly the same for a struct as it does for the components of a struct. I mean, the struct is really just this 14 bytes of memory, right?
Yes.
Because we packed it. So if we write out those 14 bytes to disk, and then we read those 14 bytes back in, we should get back the same thing that we wrote, right?
Yes.
Okay.
So what I was dealing with right there, I was kind of thinking through this. Makes perfect sense. Given that we've set aside char name, right? We've said our max here is going to be 10 characters. So that makes perfect sense.
Yep.
If
you're about to talk about dynamic, that's the second part of the talk.
Okay, I'll hold back because I think that might be what I'm getting at. Is that
yes?
Because I love, one of the things I love about C is that it's largely, from what you've explained to me, so much of this is about making things more efficient, which is why we specify how large something is, whether or not we want this memory padded or whatever, is that it's gives a lot of control. So I'm wondering,
tons of control.
If we want to say that, okay, 50, let's say we've got an array of 50 planets and 40 of them have names that are 3 characters or smaller. And there's just like a handful that have some longer names. How do we make sure that our memory is being allocated like small amounts of memory for the smaller names, larger amounts of memory for the larger names, so that we're really trying to make use of, back in the day, as you've told me, when we had no memory for anything, I imagine like every little bit of memory matters. And so the idea of just kind of saying, well, I've got 50 planets and 40 of them have small names, but oh crap, because 10 of them have longer names, I need to set aside more memory than I actually need.
I just wrote that down. That seems so
counter C.
I just wrote that down because that's exactly a kind of access pattern you're going to have to deal with. But that's getting a little bit more advanced. So for right now, we're starting with fixed record sizes. So I pinned it, so it's there for a topic.
No worries. All right. Just making sure that there's not some deep fundamental misunderstanding.
No. And you're thinking, your instincts are right. But it's going to be, let me cut to the chase. It's going to be harder to deal with it the way you just described.
Okay.
The easier thing to do is just know whatever the biggest one is and just allocate every record to be that way.
Okay.
And that's how
but
a lot
memory.
of...
But what if all I have is 200?
You get efficient later. Right now, you inefficiently write this out.
Like 1980s personality where I have no memory whatsoever. So I'm trying to you know,
Oh,
have
by
a
the
scarcity
80s, we had
mentality.
tons. We had 640K, which was enough memory
How
for
old I'm
anybody.
supposed to be? Born in the 90s, all right? That's how I got around, you know?
Okay.
Floppy disks were...
All
I
right.
love
All right.
Okay.
So how do we
Yes,
write
so-
these out? Let's get to our fread and our fwrite. So
Okay.
let's get this thing out to a file.
Oh boy.
So
Okay.
we're going to start with fwrite. And I'm just going to drop up here the part of the manual page that we have in the newer version that we don't have tonight. But if you could look it up, you would see that this is there as the description of how fwrite works. And it follows basically what I wrote on the whiteboard. So it's got that void pointer thing. Don't worry about this const. That doesn't, we're not worried about that right now. So,
Right.
So we have we have the PTR, which is going to be the pointer to the data. We have a size, we have number of elements, and we have a stream. So we have to start with the end of that, which is the stream. So how do we open up our stream?
So I'm actually going to just briefly, I know this is not the code. I'm just putting it there as a placeholder for myself. So we need fopen. And so for that, and I'm going to remember this. Give me a second. So for that, let me think back. It's been a little bit. So this is where we have the like, hold on. So file, right? Because it's a file type. And we need a pointer to that file. And so then I can define this as, this is the open. And then.
Except it's not text anymore.
Oh, what are we doing?
We're doing .bin. We're going to make up a new format.
Oh boy. Okay. And then I am writing it.
With great power
guessing.
comes great responsibility, sort of in reference to Strophium's comment here. But yeah, so...
Spider Jess. No.
Except this is... W is not a variable you declared, right?
Oh, yes. I'm so sorry.
Oh,
that needs to be...
That's fine.
That's a character. Okay.
Yep,
so
it's a string now.
String, because it can possibly be
because
the
double
plus.
quotes, not single quotes. We're not in Python. They are different here. Yeah, because it could...
the reason... Because it could have
in fact,
three technically with the
does
byte,
have
right?
another specifier if we're dealing with binary.
Does have the B.
Yep.
So I need to actually put...
Yep, this is not hypothetical. Okay.
Okay.
So now we have our FP.
Good so far?
Yep, good so far.
Okay.
Let's not check our return type. Let's just assume it always worked because nothing could go wrong opening a file. And so this is the fun version of C, like early on. So
let's see. There's a size that this outputs. So we're going to need...
I'm going to get rid of your line because you have it as a comment just above, and I'm not going to get rid of it. It's right up there for you on line 9.
But I wanted to go one by one and replace, but no, that's fine.
No.
So let's think here. When we did like fget and fput, we often had to specify like a buffer and like write into the buffer and then copy the buffer,
but we know exactly the size. Yeah.
So, okay. So we still need, because size underscore t, I'm guessing is an integer.
It's a big integer, but it's a size t. It's
so
exactly the same type that's returned by, if I want to know how big the struct was.
Size of.
Yeah, it's exactly that same type.
Okay.
In fact, I think it was added to the spec for that reason because they needed to say this is not necessarily an int. Okay. We know what file is. Yep.
Number, we have two bobs.
Uh-huh.
Size. Can I cheat?
What's cheating? Yeah. It's not cheating. That's being smart.
Okay, there's times that you told me I couldn't do that.
Oh, no. This is the time.
Okay, all right.
You should pretty much always be writing that there if you can manage it.
The void pointer.
Yeah. Well, what is it? I mean, start with what is it?
Well, so...
Like, what's missing from this line? Don't worry about the return type, by the way. So let's simplify a little bit.
Oh, I don't have to...
We checked return types last time. You know how to check return types.
Okay. So
now, like any good C programmer, you cannot check the return type.
I am learning all my shortcuts. I like this. Okay, so my intuition here, but void. Okay. It's a void because it doesn't, but we give it so.
The library doesn't know what type you're passing in. And it doesn't need to know because you specified the size.
No. Don't listen to me. Stop. Don't look.
Don't look.
No, but it's an array. An array is always inherently a pointer because an array is just a pointer to the first element in the set. So I can actually do that. And if I want to be really explicit, I can do that.
Except you're supposed to cast it because it's expecting what type?
A pointer.
Not just any pointer.
A void pointer.
Exactly. So, no, that was right. You can leave that. You can leave that. But you need to cast it. So we haven't done much casting. No, that's okay.
No. Hold on. So wait. It's expecting a pointer. If it's expecting
a void pointer. What are you passing it?
A real pointer? Struct pointer?
A pointer to a struct planet.
So this is a pointer to the first element of the array.
Hey, where did all that fun stuff you just
did?
Leave that. That's good. You did the right thing.
We haven't really done much casting. I'm not sure how to do that.
That's okay. It won't get better by removing that part. I'll tell you that much.
Okay, all right.
So to cast something, we basically just put the type we want to have it become in front of it. So we say, you should become a void pointer.
That's it.
That's what I was saying. Don't worry about this stuff. This is okay. It doesn't matter if you wrote it that way or this way. Those both refer to the same thing because the first element of Bob's is also its pointer because of the name and that handy syntax we learned. But this part is the cast, and I'm just saying that Bob's. I want you to treat that now as a void pointer.
Okay.
So listen, C. I don't want you to know what type this is. You don't care. Okay. You just care that this thing points to the right chunk of memory and each element is this big and there's this many elements.
Okay.
And send it over here to this FP thing.
Okay. Because, and let me see if this logic is correct, but if we have a pointer, let's say to something much easier like an int, it's kind of, because int is so clearly defined, that pointer, we know how much memory that address, it's pointing to an address, but we also know how much memory because it's defined. It's a pointer to an int, to like the memory address where that int is stored. But because here it takes a void because we're going to explicitly tell it how much memory to take.
And we don't want to write a version of fwrite for every type.
Right. And so that gives it the flexibility to apply to kind of any amount. That's
why we're going to treat this, that they wrote this intentionally as generic. And to make it generic, they said, this is a void pointer. It's not your first void pointer that you've seen because it was actually used in memcopy and some of the other binary routines that we did really quickly.
That's been a bit.
Yeah, that's okay. They also take void pointers because they don't care. Like they're designed to operate regardless what the underlying type is. They're just dealing with memory in an unstructured, no semantics kind of way. So they're treating it sort of as a byte stream. They're saying this byte, then this byte, then this byte. And you'd better specify how many bytes are here because otherwise I'll just read the wrong memory.
Okay.
Hey, what's up, Fafi? How you doing? And Nathaniel's right. You're basically telling the compiler that you're smarter than it, so go ahead and treat this as a void pointer. That's what casting is about. Casting is saying, I don't want you to type check this. I want you to just deal with this as it is. Now, smarter compilers come along and they nowadays say like, you know what, you're probably doing the wrong thing here. I'll let you do it anyway because you explicitly cast it, but this wasn't really a pointer to begin with, so are you sure that's what you want to do? So
okay.
Anyway, let's try this out. So what are we missing? What do we do whenever we open a file?
We close it. Oh, actually, it's been a while. Yes. Okay, so
Chat's cracking me up. F bite barf.
like barf.
Yeah, because you can kind of put anything you want
Like
in there.
barf.
You're just barfing it out as far as the compiler.
See, if I ever made a coding language, you bet that it would be hilariously named functions.
All right, well, you can F bite barf this out. So we close it, we run it,
Yep.
and things happen, right?
Mm-hmm.
Okay. Now we see no output because this doesn't show us the output, right? I mean, we ran
Right.
this thing and it just writes that file theoretically. We don't really know what happened because we didn't check the return codes, but theoretically this worked. And there was plenty of disk space, and there was no access permission problem, and all of the other things that could ever happen when we fwrite, none of them ever happen in practice, and we never check our return types. Okay, great. How do we put this back into memory? How do we resuscitate it?
Read it.
Yeah.
Okay. So now,
So let's comment.
actually, I'm gonna copy this.
All right, you can copy.
real quick for my notes. So
You can copy, and I'm going to comment.
Okay.
You can keep the file pointer.
yeah, that makes sense.
All right.
So now,
So let's start down here, and now we don't have Bob's specified. So right now we're dealing with the data. There's already been data, and we don't know what kind of data it is. So actually, I'm not going to comment it because you've never seen it. So this is something that was just passed to you on disk. All right, so this is going to be, we know that it's a planet, and we know that there's two of them because I'm keeping the example simple for now. But that's all we know.
aren't we kind of lucky that we know that much?
Well, we're going to get unlucky in a minute. That's the second half
Okay.
of the lecture.
Oh no. Okay. All right. So gracious. All right. Oh my gosh, my fingers are getting tired from all the typing today. So same thing here, but we're gonna read it instead.
Uh-huh.
And
Can we
can you
assume that
give
worked?
the
Because it could never fail.
man page for fread, or is it very
Oh,
similar?
yeah, it's actually exactly the same, but
Okay.
I will just put that here so we don't have to refer anywhere else. Okay.
Well, so we don't have struct. Nope. Hang on. Nope, we're fine. I'm good. All right.
Oh, we
makes
still have
sense.
planet defined.
Yeah. There was just a brain fart moment where I was like, wait a minute.
Yeah, we'd better know what structure this thing is because otherwise C is going to just write it however you want.
So now, so like previously when we've done this, we've been able to use like f get s and things like that, but how do we read this?
You just read it.
Well, right.
No, read.
But so the output of that, if I were to print it, for example,
Yeah,
is,
let's
is
print
a
it.
size. No, but it's just an integer.
What's an integer?
Fread returns size underscore t.
Yeah, that's how many bytes
So if I
were
want
read.
to access the data that fread has just
Where
read,
did it write? Where did it write it to? Where did it read it to? I guess I should say.
Bob's.
Exactly. You wrote it to
Okay.
Bob's. You read it to Bob's. Okay, so let's print out the first Bob's. That looks pretty good. Yep, floating point. Magic. The second Bob. Nice.
So I have a question.
Uh-huh.
A lot of the data that I use, for example, for work, I'm often not always sure until I personally like to read it in right off the bat to kind of see. It's easier for me to open, say, something easy like a CSV or whatever in Python and look at it in that format versus just opening up, say, Excel or something.
What do you think Excel's written in?
The thing, though, here is that it assumes we know the attributes of the struct, and it assumes we know, like, the data type of those attributes.
Yep.
So there's, like, a lot of assumed knowledge, whereas, like, so much of my job is dealing with data where I'm not even sure kind of what format it's in until I take a look at it. Like, this seems like a cool example to learn how to read and write stuff, but it also kind of seems like I'm really lucky that I'm reading data from a file in which I've defined the struct that was written to it, if that makes sense.
Yeah, this is real C. I mean, what you're kind of grasping at is the notion of a data description layer and intuitive semantics, because the formats you're sort of talking about, like take like JSON, for example, it's designed to be human inspectable. So you can just read it in, and it's designed that parsing it is unrelated to the data type that's in there.
Parsing is unrelated. That bothers me. Wait.
So JSON is sort of a standard in the sense that like numbers are written in like this, unquoted string form. And strings are written in this quoted string form. And you put commas between entries in an array, and you put commas between braces. Between object, like for hashes. So this notion is data descriptive, because all of that like quotes and commas and all that other stuff, that's sort of metadata. That's not directly data itself. So for example, in your example here, if I wrote this out as JSON, it would look something like,
yeah, I've used JSON before.
Bad Bob, and this thing was what, 127.5, and actually I guess these would be entries like this in some sort of array, and this would be cool Bob, and this thing would be something like 20.5. And what's neat about this is, and actually this would all be an array. Sorry, this is not a hash. So what's great about this is that it sort of has all of the information there for you to be able to parse it. Because you know where Bad Bob starts and ends. It ends in between these quotes. And you know that I'm following the same pattern for each of these entries, because I've got a string name and then I've got some sort of number. Now, I don't know what the number is because it's not specified here, but I could change my format to do that, right? I could say like, name is this thing, and then I could also say, OP is this thing. And this is kind of nice because this is data descriptive. This includes the description of what the data is sort of in the data. Well, C can do that too. In fact, most of these parsers are written in C, but the fact is that this is designed for structured data that's designed to be human readable. And I can make my format, it's sort of non-specific about what the format is. There's different types of JSON depending on what I want. This is a very loose, open format. But that's not really that efficient, because when I want to read this thing in, there could be, for example, any number of returns here. This is valid. This is also valid. This is valid. This is valid. Oops, that's not valid. This is valid. This is okay. I can put a return here. This is all still exactly the same data in some sense.
Okay.
because JSON specifies that this white space that I'm adding right now is meaningless. So it doesn't really matter if you put it there or not. Sound good?
I think so. Tentatively, yes.
Okay, well, this is also a format that's designed to sort of carry along all of the information you need to read it in.
But
yeah, what's the but?
So let's say that you write it in that format. How do I, as kind of like the ignorant reader in of that data, access the descriptions to know what format and attributes the data has?
Well, that's up to the person who wrote that data format. I mean, they would have had to give you the specifications for this data.
Okay, so it's literally it's all of this is predicated on the fact that I have this knowledge of what structure this data is in, and that is necessary knowledge. There's no way around that.
Yep.
Okay.
Yeah, C deals both with the case where you want people to be reading the data and when you sort of don't want people to be reading the data. So you may or may not include a data description. And there's different ways of specifying data descriptions, right? You could specify it in eBNF, you could specify it like an RFC, you could specify it in as a protobuf, you could specify it as, there's like a million different options. There's a long history. I could serialize the data into a CSV, but then, I get into like what happens if there's a quote in the CSV because the field has quotes and, various answers for how to escape it because it's kind of a non-standard. And then JSON, sort of a non-standard. XML, very well specified standard, very messy. Lots of different cases. But again, these formats all have different uses. But one of the things that's important is that binary data does not inherently have any description associated with it. It's just binary data. So it's up to you as the programmer to either, draft specifications or put the specifications in the file, which is kind of, there's different ways of doing that. And that all gets into like structuring data. That's like a totally different topic. We're getting into how to read and write binary data. And that's kind of this.
Okay.
Like the options you're going to have architecturally for how to store data to answer your questions about like, this is not the data that I want to parse. I want to, in fact, the more parsing you do, generally the bad, but what's nice about this, it's super fast, and by the way, all of those other formats can be built on top of this.
Okay.
It's just a question of how much work you want to do parsing it and specifying it and all that other stuff.
Yeah, fair enough.
Okay. So we've done that. We've got our Planet Bobs written out to a binary file. We read it back in and we managed to recover the same contents that we wrote out. Mm-hmm. You good with this topic?
Yes, I think so.
You inherently don't like it because this data is lacking description. It doesn't have a lot of descriptive power associated with it. It's just the raw data itself.
Mm-hmm.
Okay. And you're right. So you'll see in a lot of older formats, things like, version and you'll see like, okay, so if you're parsing this, you should be using this version and not that version. And then you'll see some magic maybe at the front, so you'll see something like some sort of like marker to say that this is this particular format. And there's sometimes you'll have a variable header, so you might have this thing which is really a struct of a header for this data, and in here we're going to include this thing and this thing and all this other magic wonder that we can get to. But that we can make our data format sort of whatever we want. For right now, we're just dealing with a uniform, single structure, very simplistic format, packed and unpacked the right way. So we know exactly what it's going to do on different architectures because we packed it. So we're sort of agnostic to padding. Now, this does get into the format, because there's multi-byte stuff in here, so it's actually not going to be super portable, but that's an advanced topic. I guess that would go into the more advanced C mess. But and yes, actually, that's Nathaniel's talking about different magic that you'll find at the front. Magic refers to like a little marker you tend to put at the beginning of a file, which tells you what you're reading.
Okay. All right.
So you can put a little bit of magic there to say like, oh, this is a PNG, or this is a JPEG, or, this is a JPEG version 3, or this is a whatever. So you can put that up front, which sort of gives you a hint about what the specification is going to be. But, you never really know if there's bad data or not. And a lot of programs have broken and been hacked because of that sort of thing. Okay. That's probably enough. I'm not going to go into the file command, but that's a program that is designed to read magic from different formats, and it has a magic database on it on your system. So
how much magic?
Okay, that's kind of the first half. So how are we're a little bit long on time for that. So should we get into the next thing or should we save it?
So the next thing you mentioned was kind of the hard thing. So my only concern is that
binary data is not easy. I mean,
just because I have that super early shift tomorrow,
yeah.
I have to be more conservative with my time. But
okay.
If you want, I think you had mentioned before, if you want to take a couple minutes just to do a preview or a next time on kind of thing, just to give a taste.
We've already
I doubt we'll have the time to dive into it
preview.
100%.
Okay. Well, all right. You know what? Let's start with a simple version of it. So I was going to go into a more detail, but let's save the harder one for, I guess, kind of next time. Do you already copy this? Should I blast it away?
Yes, I'm good. Yep.
Okay. All right. So what we really wanted to get to on this was allocators. So we already met our first allocator. It was called Malloc. Yeah, the memory allocator. Yep. All right, and Malloc. Yeah, no, that's a good guess. You're right. So Malloc does some magical stuff, and Malloc was defined in standard lib. So we got to pull in our standard library to start talking about Malloc. Okay. So how much roughly do you remember? I mean, should I just walk you through a quick version of Malloc, or should we?
So I remember from last time that we had a pointer. We were defining a pointer, and we used Malloc to set aside a certain amount of memory, but that's kind of all I remember. It wasn't, we didn't discuss it, I think, in depth, and all I really remember is it being able to we had a pointer, and I think we used a data type, and then we were able to set aside with Malloc, and then the argument of Malloc was a certain amount of memory.
Yep.
Okay, and that's all I remember.
Yeah, that's good. So if we want to allocate something like the space we're going to need for Bob's, then, let's start with just a planet. So how many bytes is planet? Well, we can find out because we can do our little trick that we know. We can say this is a size of this thing.
Malloc is the Marvel villain whose lair is the Heap.
Yes. So this is, we know now that this particular data type that we define is 14 bytes. Now, when we ask for the memory from the heap, which is kind of part of the lecture, so I was going to kind of dig deep into that, but we'll do kind of the quicker version and save a bit of that for next time. But just to kind of recap, we were basically allocating with Malloc, and we would ask for, like you said, a certain amount of memory. So how much memory do we need for a planet?
14.
Yeah. So we could directly ask for 14. And we could return that as a void pointer because you love those now.
My new best friends. Yeah.
And if we run this, it's fine. We just leak some memory, right? So we're going to assume that allocation always works, and we're going to remember to free it. And we're good to go. We wrote our program. We have 14 in there. Now we can start overlaying semantics on top of this because we know how to cast things. So we can say something like, I want you to treat this thing as a planet pointer. And this is basically going to kind of force it to be that. Like Nathaniel told you before, this is you telling the compiler, I know better than you. So I'm telling you.
do you have a misalignment or some kind of error
Oh,
if
yeah.
you try to cast something
Oh,
where the
yeah.
data types don't match
You
up?
get to keep both pieces. You're lucky if it crashes. That's one of those things about C. But dynamic memory does get kind of disastrous quickly. But we can come along and we can say, let's make a proper struct planet pointer, and we're going to call this the proper pointer. Wait, let's be more like that. Okay, so I can do that, and I can kind of get it to be sort of the right type.
Okay.
So if I execute this, yeah, we're good. We got a reference. Proper pointer knows about the semantics of planet, but pointer itself is really just a void pointer, so it knows nothing.
Mm-hmm.
So this is how we can start telling it, some semantic stuff. So we can say like, okay, I plan on treating this like a proper pointer. And if I come here and I say proper pointer, and we talk about do you remember the fancy operator for...
The pew pew operator.
Yes, the pew pew operator. Do you remember this? This is...
I don't actually remember the proper name.
This,
yes.
So I can actually use pew pew here, and I can say like, all right, let's copy in a planet, and now we're going to use some regular planets. So let's just drop Mercury in there, and we can also copy in. We can pew pew in our O period. We can say this thing is going to be, well, I don't know what I did with my data, but 87.97. All right, so I can do that, and then I free the pointer, and now we have something, we start having ownership issues. But
why do you need to free? Hold on.
Well, we allocated it. We have to give it back.
But, okay, all right.
I know to a Python programmer this is totally foreign. You're like, I just take the memory. What?
No, that's not what was throwing me. It was that, like, to me, we should... So we have the pointer, but really what we want to do is we want to free up the memory that the pointer points to. But then it occurred to me that probably free just takes a pointer.
Uh-huh.
So, yeah, I answered my own question.
Yep.
We're good.
Yeah, because we're going to use the pointer to operate on the chunk.
Mm-hmm. Yes.
So we have a chunk of memory which is doled out, but we don't directly refer to the memory. We use a pointer to the memory to refer to it. All right, so I run this. It works. We're good to go. Now, we don't know that it really worked because we didn't actually try printing it out. So we print out. All right, we're still good up to here, right?
Mm-hmm.
Now, using the proper pointer, I'm not really allocating more memory underneath. I'm still using the same chunk of memory. I'm just this is kind of like a memory view from Python world, but it's a little bit uncommon to use in Python. But this is, yeah, I can run this thing and, we're good. So I have semantics now related to that malloc.
Mm-hmm.
All right, so there's a little quick recap of what malloc and free is. Now, I can also screw myself up and double free by freeing proper pointer as well. But how many allocations were there?
1.
Yeah. How many times am I freeing that allocation? So proper pointer
is just a pointer that's like it's equivalent or equal to the pointer to for the struct planet that you set.
Yeah.
And so it's like
I already freed it.
Yeah, so you don't. It's referring to the same thing, so you don't need to free it twice. I don't know what that would even do.
You're lucky if it crashes.
I mean, what would it do if you told it to free something that you had already freed?
It's a double free. So
what does that mean?
It's kind of undefined.
Okay. Sometimes
it could crash, sometimes it could work. We don't really know. Undefined is really bad. Okay. Pointer allocation ownership gets very tricky kind of really quickly, but that is actually
ownership,
one of the
meaning what
who
is
owns
used by
this
the memory
memory
that you have allocated. Okay.
Yeah, and
not a permissions thing, but what is writing to that
memory. No, not just a permissions thing, because anybody can write to it that has a reference to it, but who is responsible for deallocating it?
Okay.
And that's where the ownership really matters. That's actually, by the way, a lot of why they made C++, because this turns out to be kind of nightmarish to deal with. And that's because of the next part, which is really what we're going to get to in the meat of the next topic. But how did we write Malloc?
What do you mean?
I mean, we have this magical function here that just sort of grants us memory when we ask it. But that had to be written in C at some point.
Mm-hmm.
So how are we implement
isn't it
something like Malloc? What's Malloc really doing?
Is it... That wouldn't make sense. So I have sort of a vague hunch, but is it kind of, it's almost like a void where it's first going to like set a memory address, and then it's casting
any memory address,
the 14 to that pointer.
No, the 14 is how big. So in this case,
yeah. So it's like that's the casting, like in scare quotes, is that it's first like pointing to a memory address, and then it's like, because before what we could do is we could cast a specific type, but in this case I'm not sure if type to me just is a placeholder for size and some semantics.
Yes.
So could you not cast a size to something?
Yeah.
Or no? So is that just what it's doing?
That's one way to write Malloc. Now the C standard is not very specific about this intentionally. Okay. So this is sort of up to the implementation. Traditionally, there were wildly different implementations of Malloc. In particular, the BSD world and the Linux world both handled this very differently. Later on, there's a lot of like kind of a renaissance around allocators, because you can build better and worse allocators. You can build them domain specific. You can build allocators that are really good at certain sizes and really bad at others. And there's kind of a world of programming there. You know, Facebook made their own allocator. You know, EA Games made their own allocator. You know, there's all sorts of like kind of famous allocators that have been written. So one of the things that we were going to do today, which is probably not a good time to start it now, is to do exactly what you just said. So that's kind of a very simple allocator. And we can do it by just basically giving ourselves a nice big chunk of memory. So we can pre-allocate a nice big chunk of memory, and we can start divvying it up as we start allocating. And that's sort of like what you're saying.
Is that the heap?
No. So the heap is a slightly different chunk of memory. So it's
so when Strophium said C quickly devolves into juggling loaded revolvers, what he really means is that C quickly devolves into juggling loaded chunks of memory.
Yeah. So
that's what it feels like, is these chunks of memory are loaded revolvers.
So we can write all different chunk handling and loaded revolver handling. Like we can, for example, a really simple allocator to build if you're ever under the gun is you can just build a version of Malloc that just keeps handing back the next chunk of memory. And when the person frees it, you just throw it away.
What do you mean by throw it away?
You never reallocate it.
That seems wasteful.
No, it's very wasteful, but it's very fast.
Why?
Because it doesn't have to reclaim anything. So there's no sizing, there's no copying stuff around, it's one of the fastest allocators you could write. It's called the Null Allocator, or it has different names. It's called the Trivial Allocator. It's very, very simple to write. It takes very few well, I shouldn't say simple. I mean, compared to other allocators, it's very simple. We can get fancy with it. We can say, okay, we have, different pages of memory, and we can say this is for chunks that are about this size, take it from this page, and this is for chunk, because this is one of those like fragmentation problems. If you start reusing the memory, you kind of want to like give the user a chunk of memory that's big enough, but where's there a big enough chunk if you've been managing it badly, and like this, there's all sorts of like nasty games you get into here.
Okay, I mean, I think that makes sense. Was because you said that when you asked me how you might implement or write Malloc, was the intuition that I had.
Yeah.
You had said it's kind of one way to do it, but then that almost sounded like
it's sort of right.
Okay.
It's one.
I know it's probably a little hand wavy because I'm missing some elements of kind of the details. But
that's what we were going to do for this part of the class. But I think we're going to save that for next time. So,
Okay.
Because I know you're on a schedule. So, and thank you, Last
5 a.m.
Miles. I
wake up.
appreciate it. Last Miles, memory, that stuff that all goes away eventually and we all swap. Yes. There's a lot of different. So again, one of those things, it's kind of easy to write a simple allocator. It's hard to write a good allocator. And it's not a one size fits all kind of problem. Different allocators are really aimed at different types of spaces. Like, you can get into arena allocation, which is pretty popular with the game developers that are around here on Twitch. So arena allocation is, zone allocation. There's we can use ropes. We can there's like, you could teach graduate courses on like all the different allocators that exist. But there is not a one size that fits all. I can tell you that. Okay. So Strophium saying that's why I historically have memory pools so that they, yes, consistent size objects and defragmentation. This is true. It's also true because they would, EA was famous about this, that they would charge the allocation to a specific part of the game. So when you were allocating memory, like you had a fixed budget of memory and that's all you got. So like the team that was working on pathfinding, this is your chunk of memory and that's all you're going to get. And when you use that up, you're in trouble. And this is one way to deal with the finite memory problem of like, how do we build a game that's going to fit into like, 256 megs of RAM or whatever they were targeting for their low end platform. And those days, I mean, these days, it's a lot more like Last Miles kind of tongue-in-cheek mention, which is that we just sort of like keep on using memory. When we run out of RAM, we just go right into the swap space, and then that's using the hard drive as RAM. And it's so and then lineup. That's you. Well, we all just Malloc from the heap and be happy, but damn it, I like my memory clean and shiny, so I always CaaAL usually. Yeah, I like CaaAL too. But we're just starting with the heap allocation. So I did want to start with a fixed size stack allocator, but we're gonna save that, I think, for the next go. So is that the hand wavy fast enough version?
I think so. Yeah, and it's a good kind of preview of what we'll be doing next time.
Okay, so for now, we're going to do just Malloc all day till we run out. That'll be kind of the memory, the Encephalosaurus early C memory allocator. We'll just go allocating and then have fun. No, you're good, Last Miles. I'm a fan of CaaAL. We didn't get into.
We just haven't gotten that far yet. So.
They're relatively simple compared to Malloc. There's some slightly different semantics that matter. I'm going to focus on Malloc mainly because I want to work on theory here. This is kind of like general C stuff, and then the other ones are really important. Realloc in particular is very important, OS and performance wise. But this is kind of getting into a more complicated than probably intro C stuff.